All right, our next topic on chapter 12 are phase diagrams. Okay, and a phase diagram is used to show the pressure-temperature relationship of all the different phases of a particular compound or element or what have you. Okay, so they're divided up into the different phases: solid, liquid, gas. All right, and it goes clockwise. If you start with solid as the closest thing on the left, go clockwise around solid, liquid, gas, solid, liquid, gas. Okay, and it's a common, probably the most common mistake when students are trying to fill out a phase diagram is to put the different phases in the wrong spaces on the diagram. Okay, so we can actually get a whole lot of information from a phase diagram, especially if we have actual delineations of pressure and temperature. All right, but this one is kind of a generic phase diagram, so we're not really going to get into those details. But we can look at what happens at each transition line. Okay, so each section of this phase diagram shows a different type of transition. All right, so if we look at the line between solid and liquid, if we're going from solid to liquid, that's melting. Right, if we're going from liquid to solid, that's freezing. Right, and the line itself is delta H of fusion. Right, if we're going from liquid to gas, we're vaporizing. If we're going from gas to liquid, we're condensing. Right, and that line represents delta H of vaporization. Right, and we can have the same sort of transitions between solid and gas. If I'm going solid straight to gas, it's called sublimating. Sublimating. And if we're going from gas straight to solid, it's called deposition. Okay, and that particular line is represented by delta H sublimation, delta H sub. Okay, so we can talk about, use the phase diagram to talk about what happens during a transition. So if I'm talking about a transition from, let's say, gas to liquid, say if I'm starting right here in the gas phase at a certain pressure and temperature, and let's say I leave the temperature where it is, and I increase the pressure. Right, so as I go along that line, my pressure is increasing, my molecules are getting closer together. When I hit the delta H of vaporization line, now I'm in the phase transition, and then as I increase the pressure, my molecules get farther, closer together and end up as liquids. Okay, so we can use words to describe processes based on what's happening in our diagram. Now, our diagram also has, let's not use yellow, red, but let's do green, has two points on it, two main points. The one where the three phases are coming together is called the triple point. Right, and this dot here at the far right on the top right is called the critical point. Right, we can also think about that in terms of the end of the phase boundary. Right, so phase diagrams are super cool. So let's talk about what's happening at both the triple point and the critical point. So the triple point all three phases are present at the same time. Okay, in equilibrium. right? So we literally have solid, liquid, and gas all present in equilibrium at the same time at the triple point. So that precise temperature, that precise pressure will have all three phases there. Now the critical point is where the liquid and gas phase are indistinguishable. Okay, we also, that's the point where we become what's called a supercritical fluid. Okay, and supercritical fluids have their own set of physical parameters and all kinds of fantastically cool things. All right, so let's talk about phase changes in terms of calculations. Okay, so remembering that heat is a path function. Okay, that means that the amount of heat that goes into a process depends on the path that we take. Okay, depending on where we start and where we end, different amounts of heat will be involved. All right, so we have a different type of diagram to talk about, which is specifically showing how temperature and energy are related. Right, so our previous phase diagram was all about temperature and pressure, but here we're going to have temperature on the y-axis and Q, or heat energy, on the x. Okay, and the way this diagram is going to look is a bit more stair-steppy. All right, so where we begin our diagram on the bottom left, this is our solid. Okay, our next sort of increase in temperature, that's where our liquid lives. And the third increase is where the gas phase lives. Right, now the flat plateau portions, and they should be flat, should show no increase. This is our solid to liquid transition. Right, and then our other flat spot, this is our liquid to gas transition. Right, so we have distinctly different areas of our graph. So notice that some of our spaces are have temperature increases. Right, so when we're in the solid phase, we have a temperature increase. When we're in the liquid phase, we can have temperature increase, and in the gas phase, we can have temperature increase. Right, but while we're in the transition phase, say from solid to liquid, the temperature stays the same. Right, the only thing that changes is the amount of heat. Right, so we have two different equations to worry about. So Q for the warming or cooling is our old friend MC delta T. Right, notice that we have a temperature change, right, warming or cooling. Our Q for a transition, say from liquid to gas or solid to liquid, is N delta H. And that may be delta H of vaporization or fusion. Okay, so depending on where you are in your diagram, you're going to use different equations. So let's say that I'm going to start with a solid at a given temperature. And I want to end it I want to add enough heat so that I end it as a gas of a particular temperature. Right, so first I'm going to warm my solid. Then I'm going to melt my solid. Then I'm going to warm my liquid. Then I'm going to transition to gas. And then I'm going to warm my gas. Okay, so there will be 1, 2, 3, 4, 5 separate steps to this process. Now let's talk about delta H really quick. So delta H, let's say delta H of fusion. Sorry, lost my place in my notes. Okay. So delta H of fusion, that's for melting. And it'll be given as a positive value. Right? So if I want to talk about for freezing, I need to flip the sign. So freezing will be negative delta H of fusion. Right, so remember that opposite processes have the same magnitude, just opposite sign. Right, same thing with delta H of vaporization. That's for vaporizing. So for condensing, will be negative delta H vaporization. Okay, and if that's hard to remember, remember whether you have to put energy in. I don't think that's how you spell that. Or take energy out. Okay, that will help you remember what sign delta H should have. So if I'm melting something, I should be putting energy into it. Right? If I'm freezing something, I should be taking energy out. So putting energy in will have a positive value, energy out will have a negative value, just like money from your bank account. Okay, so we're going to go ahead and stop this video right here. When we come back, we're going to do an example problem where we go through the steps to calculate a phase change.